Assalamualaikum, my name is Mat575 Vid Presentation and my partner Siti Aisyah binti Zaini. Today we would like to present to you about our topic, which is Department of Fisheries.
Let's start with introduction. Our main objective is to provide a solid technical plan that protect the environment, prevent disease, and ensure high quality fish production. To achieve this, we must maintain an optimum oxygen level of above 5 mg per liter to improve the survival rate, health, and growth of siakap. To prove this, our study analyzed 20 data points. In this dataset, the independent variable is the dissolved oxygen level and the dependent variable is the siakap survival rate, which is used to measure final harvest yield. For the analysis, we test two mathematical models to find the best fitting function, the least square linear function and the least square polynomial function. We compare their SSE value to confirm which formula is the most accurate. Based on the data, the Department of Fisheries requires farm to be located away from alga bloom and to use paddle wheels adjust by fish weight. To prevent stress cage farming, density must be 0.4 to 0.7 kg per cubic meter, while pond farming must be lower between 0.03 to 0.1 cubic meter. This slide shows our data for linear function. On the left, we plot our 20 data point into a scatter plot graph. As you can see, the trend line goes up in a straight line, proving that highest oxygen levels directly lead to a higher fish survival rate. The linear equation generated from this graph is y equal to 12.375x plus 20.85x. On the right, we have our calculation table showing the summation of x, summation of y, summation of xy, and summation of x squared. We will use this total number to calculate our final SSE value for these linear models. Moving on the calculation process, this slide details the 5 steps used to solve our linear model. In step 1, we establish our base linear curve equation using degree m equal to 1, which is fx equal to a naught plus a1x. In steps 2, we set up the normal equation into a 2x2 matrix. The formula is matrix of n, summation of x, summation of x, summation of x squared times matrix of a naught and a1 equal to matrix of summation of y and summation of xy. In step 3, we calculate the coefficient by inserting our total value for the SL table into the matrix using n equal to 20 data point, which is matrix of n equal to 20, summation of x equal to 101, summation of x equal to 101, and summation of xy is 524.6 times to matrix of a naught and a1 equal to matrix 1667 and 8519.8.4. In step 4, we solve this simultaneous matrix equation to calculate the exact value for our unknown, given us a naught equal to 20.858 and a1 equal to 12.375. Finally, in step 5, we substitute this calculated coefficient back into our original formula to get our final best fitting linear function, which is fx equal to 12.375x plus 20.858.
Alright, now let's move to data for quadratic function. This data presents our data sets for the quadratic function analysis. On the left, we have plotted our initial XY data points along with a linear trend line. On the right, we have prepared a full calculation table extending our variables to include xy, x squared, x cubed, and x to the power of 4. This data setup gives us all the necessary summation values required to construct and solve our least square regression matrix for a quadratic curve. Moving on to the next slide, there are 5 key steps we followed to complete our least square regression analysis. First step, we define our polynomial degree as m equal to 2 to establish the standard quadratic curve equation, which is fx equal to a nodes plus a1x plus a2x squared. Step 2, we organize this normal equation into a structured 3x3 matrix format. Start with n, summation of x, and summation x squared for the first row. The second row is summation of x squared, and summation of x cubed. The third row is the summation of x squared, summation of x cubed, and the last one, the summation of x to the power of 4. On the right side, we have the summation of y, the summation of xy, and the summation of s squared y, x squared y. Step 3, we used our total sample size of n equal to 2, equal to 20. We took the summation values calculated in Excel and substitute them directly into the matrix elements. For the value of n is equal to 20, the summation of x is equal to 101, summation of x squared equal to 524.6, summation of x cubed equal to 2,795, and the summation of x to the power of 4 is equal to 15,228.29. For the value of summation of y is equal to 1,667, summation of xy equal to 8,598.4, and the last one, the value of the summation of x equal to 2, the summation of x squared y equal to 55,506.24. By solving this matrix system, step 4, we successfully calculated our unknown coefficient yieldings A0 equal to negative 52.614, A1 equal to 42.587, and A2 equal to negative 3.0156. Finally, in the last step, step 5, we will substitute this precise coefficient back into our original model to produce our definitive fitted quadratic curve equation, which is fx equal to negative 3.0156x squared plus 42.587x minus 52.614. Now, let's look at this image. It presents our final model comparison and error analysis. In the data table, we have calculated the predicted values and the sum of square errors, or SSE, for both our least square quadratic function and the standard linear function. As highlighted on the right side of the slide, the total SSE values for our quadratic function is 7.1152, which is smaller than SSE values for the linear function, which is 76.5086. This clearly proves that the quadratic model or polynomial order 2 provides a much better and more accurate fit for our data. Now let's move to the conclusion. First, higher dissolved oxygen improves sea carp survival, but the improvement start to level off at higher level. So what does this actually mean for the fish? Simply put, more oxygen means better survival, but there is a catch. The quadratic model shows a slight curve because of that negative coefficient. This tells us that adding oxygen helps a lot at first, but after a certain point, the benefits start to slow down and level off. Next, meeting official standard, dissolved oxygen greater than 5 mg per liter is critical to reduce fish stress, prevent mortality, and maximize sea carp survival. To back this up with official standards, both the Departments of Fisheries Malaysia and SIRIN state that dissolved oxygen must be kept above 5 mg per liter. This isn't just a random number, it is the baseline required to keep sea carp healthy, growing, and alive. By maintaining this level, fish farmers can drastically cut down on fish stress and prevent sudden die-offs in their aquaculture system. Last but not least, managing dissolved oxygen properly is the single most important action to prevent fish die-offs and maximize sea carp survival. To wrap everything up, both of our models clearly prove that dissolved oxygen is a major factor in sea carp survival. The linear model shows us the big picture. It shows that more oxygen leads to better survival. But the quadratic models give us the finer details, showing exactly how that survival rate behaves at different oxygen level. The ultimate takeaway here is simple. If we want to improve sea carp survival and stop fish die-offs, proper oxygen management is not optional. It is absolutely essential.